Well, welcome everybody this afternoon, the Aspen Center for Physics Public Lecture. As Emily pointed out, my name is Gordon Boehm. I'm here to represent the center. While my day job is teaching physics in the cornfields at the University of Illinois, I've been a participant in the center for many, many years, as Emily pointed up, and the part-time resident of Aspen for many, many years as well. For those of you who are not familiar with the center physics, let me say the center plays an extraordinary role in the lives and progress of the community of physicists. Each summer, well over 500 leading scientists from all over the world come here for a few weeks at a time, do research on current problems, physics, with virtually no distraction, except, of course, for the mountains, the music, and they have all the other good parts of life in Aspen. And the center, in fact, is like our summer camp for group of physicists. Once becoming altitude adjusted, it's really quite wonderful to discuss physics while walking in the country here. The lecture series is held in memory of Heinz Pagels, the wonderful physicist and friend we lost in a tragic mountaineering accident in 1988. I'm very happy to see Heinz Pagels' wife, Elaine Pagels, who is here today. She's a distinguished historian of religion. Let me mention, if you'd like to be informed about future events at the center, please add your name and email to the mailing list on aspenphys.org, which is listed on the back of your program. Or if you prefer to use Stone Age technology, you can write it down at the front desk as you leave. Yep. The list is safe. It's not shared with anybody. Well, it's a particular pleasure today to welcome this afternoon speaker Joan Najita, noted astronomer from the National Optical Infrared Astronomy Research Laboratory in Tucson, Arizona, known as the Noir Laboratory. So that's much more mysterious that way. Joan spends her time trying to figure out how stars form interstellar clouds and how disks surrounding young stars evolve to produce planets, which tell us about today. Interests range widely over astronomy, from how young stars produce the chemical ingredients life, to the life history of the Milky Way, of nearby galaxies, to more general topics, including how discoveries are made in astronomy and developing new research tools and facilities that sustain discovery. Joan earned her BA physics at Harvard University, and then her MA PhD in astronomy at the University of California in Berkeley. She's played a very important role in the governing the Aspen Center for Physics, being one of the 80 members here for quite a while. She enjoys communicating science to the public and has a lifelong interest in the power of science to inspire and the role of science in society. Some of you may remember her work with the Spring Concert, Musica Universalis, of the 2022 Aspen Choral Society, connecting images from the Hubble telescope, the music itself. Today, she will tell us how did we get here, the origin of stars and planets. We're all looking very forward to hearing about. So welcome, Joan.
Thank you, Gordon, for that very kind introduction. Thank you all for coming out today to talk about science. I'm Joan Najita from NSF's Noir Lab. And as advertised, my title today is How We Got Here, the Origins of Stars and Planets. Before getting started on my topic, I thought I'd give a quick introduction to the mysterious organization that I work for, Noir Lab. So what is Noir Lab? It is the National Science Foundation Center for Optical and Infrared Astronomy. Based in Tucson, Arizona, our mission is to develop and operate forefront research facilities at Kitt Peak National Observatory, shown here. Also, to create and serve frontier data sets, as well as the tools that can be used to analyze those kind of data sets. This is all in the service of the idea. Anybody with a good idea should be able to pursue that idea using forefront research capabilities. So that's what we do. But today I wanted to share with you some of the research that some of us are engaged in, thinking about the question of how we got here, our story. And this is a topic that astronomers love to think about in all different angles. Some of us think about the origin of the universe itself, how the small scale structure from the very beginning of the universe gives birth to galaxies. Other people think about how within galaxies stars are created and the planets that surround them. Some of us even go a little bit further, think about origins of life. Well, this is clearly too big a topic for one short talk. So today I just wanted to focus on one small part of this picture, origin of stars and planets, but mostly planets, the one that we live on. You might be wondering whether there is an origin story here. Is there a beginning? Because when we look out at the sky at night, we see beautiful panoramas of stars, look pristine and eternal, like they've always been here. Not really. Actually, stars are born, they evolve, and so do the planetary systems that orbit them. In our own solar system, of course, we have our familiar terrestrial planets, Mercury, Venus, Earth, and Mars. On the inside here, I'll use my little pointer, and our gas giants, Jupiter and Saturn, and our ice giants, Uranus and Neptune. So we might wonder, how were those planets made? And why is the solar system unusual or not? And why? So today, I thought maybe we could have a quick look at the classic picture planet formation, how we once thought this all worked, and then talk about some of the new insights and new questions that have come from observing the universe, from looking at planets, other solar systems, the birthplaces of planets going on today. And then if time allows, I'd like to just touch on a little bit about the topic of how discoveries are made in astronomy. So think about classic picture of planet formation. The way we can get a really good clue to the answer to this question is just by looking at the night sky. When we look out in the night sky and find the planets, find that they are located in a line on the sky, which is really a plane, three-dimensional space. That gives us a clue. The planets formed, solar system formed in a flattened disk, gas and dust. By dust, I don't mean the stuff that collects under our beds, those dust bunnies and things. No, I mean small particles of icy salts and ash. Our question today is, how do we go from this flattened disk of gas and dust to the planets we know of? Well, this is an amazing story that extends over many orders of magnitude, the core accretion story. And it includes everything from the smallest things in the solar system, the biggest. The story goes like this. Start with the smallest things, tiny dust grains, maybe a micron in size, that collide and stick together to make bigger dust grains. Those dust grains collide and grow to make pebbles, and a meter in size of objects. Those pebbles can collide and grow too, but more likely they get together through collective effects called instabilities, produce really big objects. These called planetesimals, a kilometer to 100 kilometers in size. When those objects enter the inner solar system, they develop beautiful tails and we see them as comets. But most of the time they're forming planets, they're out further away where they look like dirty snowballs. Those planetesimals can collide and grow to make what we call protoplanets, maybe 1,000 kilometers in size. The moon or Mars would be an example of that. Those can collide and grow to make things like the Earth. Wait, there's more. Things that are the Earth, size of Earth, can collide and grow too. And if they get up to be 5 to 10 times the mass of the Earth, they can have the chance to enrobe themselves in a little bit of the gas that's in the disk. And if they grab a little bit of it, they make an ice giant like Neptune. If they grab a lot, they end up as a gas giant like Jupiter. So that's the basic picture of core accretion. We astronomers love it because it explains a lot of things, like how it's possible that in our own solar system, we can have very different kinds of planets, the terrestrial planets, gas giants, and the ice giants. But when you think about this picture, you know, really we're getting these insights from looking at the solar system middle age. Solar system's neither very young or very old. We're just looking out at what we see today, trying to infer everything about its history back to when nothing was there. You might wonder, thinking about our own history as humans, do we really look at ourselves in middle age, then trace back to where we were the very beginning? Maybe not. So astronomers are concerned too. That's why. That's why we go out and test these ideas, looking for other clues out there where we might be able to, say, study the birthplaces of planets, where planets are forming today, using those observations as kind of like a machine to go back in time to see what our own history was like a long time ago. Might also try to look for planets around other stars, learn what are some other outcomes of the planet formation process. By looking from early to late, might be able to trace out the evolution of planetary systems, put our own solar system in context. One of the first things you might wonder about is the very beginning of this whole story. Those flattened disks of gas and dust. Where do they come from and do they really exist? Well, the reason we think that they're there is because when we look out in the night sky and you see these dark regions over here, these dark clouds, inside those dark regions are what are called molecular clouds, made up of gas and dust. They have clumps. The clumps are not just sitting there, but they're rotating a little bit. They're huge. So when they collapse under gravity, just like how an Olympic skater, and their arms are, they might be rotating slowly, but when they pull their arms in, they spin up quite a bit. Material that falls in from a molecular cloud has too much angular momentum to fall right onto the central star. A lot of it goes into orbit around the star, the flattened disk, gas and dust. And material in the, me indicate with my pointer here, material falling in spirals in from the outer disk to the inner disk, eventually making its way onto the star. That's part of the story of how the star builds up its mass too. And while the material is spiraling in from the outer disk to inner disk, it has a chance to make some planets. That's the theory. Is it really correct? Nice to find that out. So we were really excited way back in 1992 when the Hubble telescope looked at the Orion Nebula. So here's the familiar constellation of Orion, its shoulders, legs, the belt, and the sword. It looked at the Orion Nebula and took pictures of young stars that looked like this, something that looks a lot like a theoretical picture. What's going on in this picture? Well, we've got a bright young star here shining brightly, and the disk looks dark because the icy soots and ash in the disk are absorbing the light from the background Orion Nebula, making it look dark. Now, there are many other disks like this out in the galaxy. To see examples of this, you actually don't have to go very far. You might look at a mug, a calendar, or maybe a screensaver, because these images of where stars and planets are forming are some of the most popular in astronomy. So here's a picture of the pillars of creation, Eagle Nebula, um, uh, observed by the Hubble Space Telescope there on the right. And a new version of this, a portion of this region, imaged by the James Webb Space Telescope. And deep in these molecular clouds are some young stars surrounded by disks. Another region that is pretty popular that you may know of is the Head Nebula in Orion. There's a picture there taken on the right by my observatory, and here on the left is a picture taken by the Hubble Space Telescope. Deep in this molecular cloud are also some young stars surrounded by gas and dust. There's many disks out there in the galaxy. Should be pretty simple. We go over there, we look at them, and see what kind of planets they're forming. Well, not so fast, because theorists have imagined all kinds of things that could go wrong. Our great theory might actually fail. So, just want to share a couple of those disaster scenarios with you today. So, one idea, when I was a grad student, my colleague, who was a brilliant astrophysicist, I asked him, what'd you do over the weekend? He said, I made Jupiter. Jupiter into its disk, reached out with its gravity, it exchanged angular momentum, and it spiraled into the sun and was gone. So I said, what did you do next? Well, I did it again, put it there, exchanged angular momentum, spiraled into the sun and was gone. He said, my best theory is that Jupiter was born, it migrated into the sun, and it doesn't exist today. It's not a very good theory, and a problem that many people have wrestled with. Another problem is that our favorite little pebbles, which we're eventually going to try to make some planets, well, they actually, there are aerodynamics, they're embedded in this gaseous disk. They feel some headwind from the gas. So they're trying to slow down, and that makes them lose angular momentum. And they were also thought to spiral into the central star. Then we would have no resources left to make any planets. So, oh my gosh, might not be able to make a planet. And then even if we could, it might not survive. So for many years, people thought, well, this is the reason we're not finding any exoplanets out there. But when confronted with these challenges, theoretical challenges, what should astronomers do? What we always do, which is to just go out there and observe the universe anyway. Today, I wanted to share with you some of the things that new insights, observations that have been made, and the new insights that people have gotten from observing the universe. First, looking at the region pretty close to the star, within the orbit of Jupiter. I just want to give 3 stories. Close to the star, within the orbit of Jupiter, farther from the star, beyond the orbit of Saturn. Then what I'd like to call the awkward middle region, the most difficult, between Earth and Saturn. Let's have a quick look and see what we can learn. Starting really close to the star and try to find some planets. Now, you may know that, in fact, planets have been discovered around other stars, and the technique by which the first planet was discovered around a normal star was the precision radial velocity technique. Here we've got a star surrounded by a planet. The planet feels the tug of the star, goes in a big circle. The star feels the tug of the planet, goes in a little circle. The star is a lot easier to see than the planet, so astronomers try to measure the little wobble of the star. With this technique led to the detection of the first planet orbiting a normal sun-like star way back in 1995, which this group of astronomers won the 2019 Nobel Prize in Physics. Ever since then, people have been using this technique to characterize planets, and so far, looking at the total number to date, something like 1,000 planets have been studied this way. The real champion in terms of total numbers of planets that have been studied, the so-called transit method. What is that? That's a really cool method too. And the champion is probably the Kepler Space Telescope there. And in this method, we imagine a star. Let's make it big so we can see what's going on. A planet passes in front of it, blocking out some of the planet's light. By looking at how much fainter the planet gets during this transit and how fast the planet goes across, you can infer some properties of the planet. What kinds of planets have we discovered these 2 methods? Illustrate that. Let's make a plot. And so on the y-axis, let's plot the mass of the planet. And on the x-axis, let's plot the distance from the star. For reference, let's just put the planets in our own solar system. So we've got Earth over there, and Neptune, and Jupiter. What are the planets compared to those? Well, they're over here. So you can see here that there's a lot of planets up here that are more massive than any planet in our solar system. You can see that one of the most popular planets is down here between the mass of the Earth and Neptune, a so-called super Earth. Nothing like that in our solar system. Perhaps the most overwhelming impression of all this is that most planets are a lot closer to their central stars than any planet in our solar system. All these solar systems, they don't look like ours. Is our theory wrong? Well, actually, no. We can imagine that planets form where we think they do, then they migrate in by that old problem that we had. Perhaps we can turn anxiety into a solution. So that's, in fact, what astronomers think, that our old problem of how Jupiter went right into the sun be a way to move the planets to where we see them. In the meantime, we've also learned that the disk that the planet is embedded in really doesn't extend all the way up to the star. It's truncated by the stellar magnetic field of the star. So there's an inner edge where planets should stop. And when we look at the distribution of these planets, we see that there's a bunch piling up here. The location of where the disk is truncated, perhaps we're seeing the imprint of the planet's formation environment on the demographics of the planets that we end up with. So we seem to have learned something here. First, that planets around other stars can be much more diverse and very different from our own solar system. Our original picture that we developed just to explain the solar system could also apply all these other systems if we make our explanation more dynamic. We allow planets to move after they've formed. That can produce the much more diverse systems that we've discovered. And as humans developing our theories, I think we also learned that some of our things that we consider to be problems also turn out to be solutions. To keep that in mind. These observations also raise some new questions. Or its planets could stop when they get close to the inner disk edge, but there's a lot of planets at all these radii. So why do those planets stop migrating? Also, why do we have this? Why does the solar system have the planets that we do, not others? Like, we don't have a super Earth. So, understanding our questions about planet formation have moved from how do I assemble a planet, understanding the architectures, planetary systems. Why are the planets where they are, and why do they have the masses that they do? Good. So that's a bit of what we learned from the very region really close to the star. Let's have a look at what's going on much further from the star, beyond the orbit of Saturn. And this region of the disk is really undergoing a kind of a revolution. Because a long time ago, when we had these pictures, these were the state of the art. We used to think that, well, these disks look very smooth, very pristine, very primordial. You're just about to start doing some planet formation, maybe in 100,000 years, sometime, not now. Well, this picture became increasingly untenable the more planets that were discovered. So, more and more planets. And we think that if the disks are going to be the environments in which all these planets are born, then they have to have enough resources, enough mass, to make all those planets. All as people discovered more and more planets, it became pretty clear there was more mass in planets than in the dust and pebbles in the disk. So, is this a problem? Are these disks not the places where planets form? No, more likely they are. They're not at the beginning of their process. They're already using up their resources to build planets, and that's why we have so little dust and pebbles left because they've already converted some of that mass into planet. So, it was a kind of a revolutionary idea 10 years ago, but it was confirmed quickly when a new facility came online. Atacama Large Millimeter Array, located on the Chajdantor Plateau in Chile. This facility, called ALMA, is made up of many individual radio dishes that together make high angular resolution images of the universe. So when ALMA turned its eye to look at a very young disk, and that people thought could not possibly be making any planets, this is what it saw. So the young star, HL Tau, had an incredible amount of structure. Rather than a nice smooth disk that we'd always imagined, it showed luminous rings of millimeter emission. That's where the pebbles are, separated by dark gaps. With the size scale of these gaps comparable to the orbits of the giant planets in our own solar system. So this picture here, these rings are the orbits of Jupiter, Saturn, Uranus, and Neptune. Very similar kinds of sizes, and more amazingly, exactly what we had imagined a planet-forming disk would look like. Before we made these observations, people would make artist conceptions of what's going on in these disks. That picture up there is one of the beautiful pictures that people had made, where a planet forming in a disk clears out the material in the vicinity of its orbit. We see something very much like that, the HL Tau disk. Kind of amazing. Well, HL Tau was the first disk to be observed, but many others have been observed since. And as you can see here, rings are a big theme. Sometimes we see thin rings, multiple rings. Sometimes the rings are thicker. There's a lot of rings. This is a good thing because it helps us to understand why our old pebble drift problem is not really a problem. The picture where pebbles lose their angular momentum through aerodynamic drag and spiral into their central stars, it assumes that the disk is very smooth. But when the disk has a lot of structure, something else happens. These rings are enhancements of density, and pebbles, it turns out, love to collect where there's an enhancement of density. It's all about the aerodynamics of how that works. But as an analogy, we could imagine we're shopping at a supermarket, at our cart, I need to go over there to the vegetable section, but whoop, I see some free snacks over here. Maybe I'd like to stay here a little while and taste that and see what else is going on here. It's like that. Pebbles love to congregate where there's an excess of gas. And by bringing all the pebbles together, it means that all the resources for planet formation are much more concentrated. That really can speed up the process of making planets. It can help us to understand how we could possibly make planets of large radii. For their understanding of this process, how to solve the pebble drift problem and the implications for planet formation, these 4 young astronomers won the 2024 New Horizons Breakthrough Prize in Physics. We're pretty excited. It's a big deal for physics. We're also really excited about these rings because of what they might tell us about the planets, these disks. Because our little diagram here, our imagination, we're imagining that planets clear out these gaps in the vicinity of their orbit. And so when we see rings, also imagining between the rings are some planets. Clever theorists can use the structure of those rings to infer what kind of planets created them. When we put those planets on a diagram, this is what we see. Here's our old diagram of planet mass on the y-axis, distance from the star on the x-axis. These gray points are those same planets from the inner solar system that we were looking at before. And we also have our reference points in the solar system, Earth, Neptune, Jupiter. And the funny symbols out here, are the planets that we infer from the structure of those rings. You can see here too that these planets are pretty unusual. Many of them are more massive than any planet in our solar system. And many of them are at larger radii, further from their star, any planet in our solar system. Another example of the incredible diversity of planetary systems out there. These are hypothesized planets. Would really love to confirm they really exist. People have been looking really hard, these images, in deeper, more careful observations to try to find those planets, and it's actually been difficult to see. We think that may provide some important clues how planets are really forming. But I'm happy to say we were able to find some planets in at least one disk. Young disk, PS70. So here's an image taken with ALMA of the pebbles in this system, which is in this big ring. And this little dot here is the young planet. This is taken at millimeter wavelengths, but we could also image this system shorter wavelengths in the optical, where we see not one object, but 2. Here's PDS-70b over here, and PDS-70c over here. People are so thrilled to see this, even made a song to celebrate this. I thought we could have a quick listen. The track created by the instrumentalist Sleeping at Last. That's called PDS-70b, Birth of a Planet. In their astronomy collections. So, getting back to interrupt the musical interlude, but to wrap this little piece up, this little piece of the story, it's pretty similar, as you can see, to the first piece, in the sense that learned from studying outer solar systems, planetary systems are even more diverse than we thought. They were diverse on the inside, diverse on the outside, quite different from the solar system. Also, that what we learned from these studying the outer solar systems are that planet formation can be much more dynamic. That rather than planets can move, we learned from the inner solar system, but the ingredients that make planets can also move. These pebbles can migrate over large distances and assemble in rings, sparking the formation of planets. And that helps us to explain why we could possibly have planets at very large distances. It would be difficult to understand otherwise. Similar to the first story, we also learned that the things that we were afraid of, pebble drift, also become a solution. While we've learned some new insights, we also have some new questions, as I indicated. One question is whether these planets that we've been inferring, whether they really exist. There's a bit of a chicken and egg kind of problem going on, as you might have noted. Because I said one of the ideas was that planet clears out a gap in the disk, making these rings, but we also needed the rings in order to assemble the pebbles to make a planet. So, kind of a chicken and egg thing. You need the ring first, or do you get the planet first? People are trying to have many ideas of how to solve this problem, and a lot of activity is going on in this area. So, we looked at the inner regions and the outer regions and found some interesting things. Let's have a quick look at what I like to call the awkward middle, the mysterious part of the whole story. We really don't have as much information about. It's the middle in two senses. First, the middle radii, between smaller than the orbit of Saturn. The reason is, when we look at this image of HL Tau, region within Saturn is basically this central yellow dot. Just don't have a lot of angular resolution there. We don't have fine vision, see all the details that are going on there. So it's a bit of a mystery. Another part of the mystery is the middle sizes. This one is kind of worrisome at some level. Because when we talk about building the solar system from the smallest things to the biggest things we can actually see are at the two ends of the story. Dust and pebbles, see that? Jupiter, self-luminous, might be able to see that. All the middle things, planetesimals, the protoplanets, even the forming Earth, they're like big rocks. Not so easy to see. Once you go from the small things to the awkward middle, become like a kind of dark matter that we can't see. It's not the cosmologist kind of dark matter that we don't know anything about. We know what this is, but we just can't see it. And that's kind of a problem because we would like to confirm that our picture really makes sense. Another way to think about it is going back to this image that we looked at the very beginning. What do we see here? We see stars that are shining from nuclear fusion. They're casting their own light out into the universe, and they're illuminating small dust grains that we can then see. If I took all those small dust grains and I crushed it down to the density of a rock, it would be pretty hard to see that. And that's the problem, or the awkward middle. How do we solve a problem like this? It's pretty tough. Well, maybe we can be a little reach out there and try to use some chemistry. I just want to sketch out how this might work. Be speculative. You remember that disks are made out of gas. Let's call them pebbles, right? And what are those gas and pebbles made out of? Well, the gas is made mostly of hydrogen. It also carries the active carbon. Solids, they're far out in the disk, so they're cold. The water freezes onto them. Icy grains. How do these things move? Well, we know that the gas is going to spiral on its way to the star. The pebbles are trying to get there even faster because that was the pebble drift problem. So, in a disk with no planet formation, the result of this process is to make the inner disk become oxygen rich because it'll have a lot more oxygen moving in there. What happens when we make planets? Are in the same place. Now let's convert our pebbles into planetesimals. big objects, kilometer, 100 kilometers. They don't notice the gas moving by them. And when they form, they just sit there. Okay, so then our dynamics will be quite different. Planetesimals are just sitting there and the gas is moving in. The gas is carrying the active carbon. So, in a disk with planet formation, you should expect to see a disk become more carbon rich on the inside. So, oxygen rich, no planets, carbon rich, planets. We might be able to detect that if we can measure the chemistry of the region of the inner disk region. We gave that a shot with our old ST space telescope, Space Telescope, where we looked at the inner regions of these disks and dispersed their light into a rainbow. We're with enough resolution to be able to get some chemical fingerprints of what that disk there is made out of. We were thrilled to find things like water and simple organic molecules, acetylene, hydrogen cyanide, carbon dioxide. And more interestingly, the chemical signatures showed an interesting pattern at disks that are more massive, the ones that are more likely to be making planets, also with more carbon rich on the inside, like we kind of imagined. This is just a hint, of course. So the idea has always been to try to use more powerful telescope like James Webb Space Telescope to confirm these ideas. And indeed, Webb is out there observing cosmos, but in particular, these molecular clouds, looking at disks, dispersing the light from the inner regions of these disks, see what's there. Story's still being written, the data's still coming in. I don't have the answer at the haven't gotten to the end of the story yet. Can't say Webb is finding some pretty amazing things. So in our original observations, we could measure very small molecules like water, hydrogen cyanide, acetylene, carbon dioxide, things like 3-4 atom molecules. Recent observations with Webb have shown a much richer kind of chemistry. There's methane, a 5 atom molecule, methane, ethane, 8 atoms, propane, 7, acetylene, 5, and others that I got tired of typing those in. And in some cases, we also see a 12 atom molecule, benzene. Well, are these super carbon rich kind of chemistry? Is that the fingerprint of planet formation? Or is it something else? People are trying to figure that out. Hope we'll have more to say in the near future. Just taking a big step back from all of that. Basically, we are measuring the chemical composition of planet formation regions where planets are formed, planets like Earth. That ability to measure the chemical composition makes us think that, well, maybe in the future, we'll actually be able to start addressing questions like this. What kind of chemical building blocks planets really inherit? That's something probably in the far future. It's interesting to think that we might be making some baby steps toward that today. So maybe it's a good time to kind of sum up where we are. How did we get here? Well, it turns out that old theory, core accretion, from looking at the solar system at middle age, isn't too bad after all. We only had one system to look at. It seems like it can explain a lot of what we see out there if we're willing to make the system a lot more dynamic. When we make a planet, we should allow planets to move, when we should be able to move our resources together, form planets more quickly. When we do that, turns out we can explain a lot more diverse systems. And that story, migration and assembly, is perhaps a little bit like how humans are created. Because each of us, the product, the places we've been, things we've seen, the things we've done, as we move from place to place, we're also the recipients of a huge amount of cultural history that has come from maybe far away, maybe over several generations. And all of that together is where we are today. Planets are similar. They're the product of wherever they've migrated to in the disk, and they've also been the recipients of a lot of accumulated resources in those pebbles. Now, kind of interesting that there may be a parallel between us and the planets out there. Another thing that we've learned about ourselves as humans trying to understand the universe is that we shouldn't be too afraid of our fears. Things that were scary before actually turned out to be inspirations. And the ability to flip that around is an important part of how this theory has developed. So if we were to make a little equation for the history of this topic, it might be old theory of core accretion plus our old anxieties, which became solutions, led to a new, more powerful theory, greater explanatory power. So if that's where we've been, where are we going? Just a couple points to think about the future. As I indicated, early ideas were about how to assemble the planets, but now we're trying to think about the architectures of planets, planetary systems. Why are some planetary systems like this, and why are others a different way, and why is the solar system the way it is? And I was able to here just talk about a few of the main ideas that people have been thinking about in planet formation, but there are many, many more. And I hope I was able to convey that one of the challenges and opportunities for the future is trying to figure out how those ideas really fit, like pieces of a jigsaw puzzle make a really good theory. That's the way this field will probably progress. One of the fun things to look forward to. Of course, there are things that we really don't know that much about, like the mysterious middle. Like maybe some of the ideas that I suggested will be the ways forward, but maybe it'll be something else. But I think that the ways forward will be right around the corner, because as I've tried to show, this field is very fluid and very discovery oriented. And so new things will be happening all the time. That said, I think we have just a couple more minutes. And so I wanted to take another step back and look at how the things that we've talked about today might tell us a little bit or give us a flavor of how discoveries are made in astronomy and science. And because time is short, I'll just say what I kind of think about that. Okay, so I hope I was able to show that, illustrate how, although astronomy is one of the oldest sciences, it's also extremely youthful in the sense that discoveries are being made all the time and in many different ways. You can make discoveries involving large teams of researchers or by small groups and individuals. You can make discoveries state of the art resources, very modest ones. And sometimes discoveries are driven by technology, also sometimes by very human elements, things like our curiosity, our extreme persistence, the new ideas that different people bring to an enterprise. Some of the examples that we looked at today sort of illustrate that. Discovery of the first exoplanet was made by a small group using relatively modest technology, but it spawned a new field of astronomy that's one of the most rapidly growing and popular today. This example, you had a bunch of people working as individuals in small groups, sometimes in teams, all looking at it from a different point of view. These ideas all came together along with the arrival of a new facility, ALMA, has really turned this into a really popular, rapidly growing topic. And over here, in the mysterious middle, this discovery was just by two people, really wanted to know what was going on with the chemistry in this disk. And even though the instrument builders didn't think it was possible, and the community of astronomers didn't really think it was possible either, they just did it and showed that it's actually pretty easy. And that has spawned a new area of research as well. Even though these are just three isolated examples, they actually bear out the general trends from a much larger collection of information, all kinds of science. We look at the citation statistics that come from looking at literature, scientific literature, and patents. We can tease out the general trend that the most innovative results, most disruptive discoveries are generally made by individuals in small groups And it's large teams that can then take those ideas, build them, and push them to their ultimate, fruition. In order to sustain discovery, we need to be able to sustain both of these modes of working, both small groups and large teams. That's why I love the Aspen Center for Physics, because that's what it does. It makes it possible for individuals and small teams to do some creative work here. It also brings people together. They can share ideas and build those teams that are needed to get where we need to go. So I wanted to thank the center for all the work that it does, and to thank all of you, your interest in science, for coming out today. Thank you. Yeah,
Many questions.
go ahead.
We have a number of ringed planets in our solar system. How do they fit in as far as maybe this middle round and the formation of little moons and spaces in between that?
Yeah, actually, fantastic. So, back here, when we were looking at the planet, where is it? Okay, so back here, when we're looking at this picture taken by Alma of PDS-70b, and it is glowing, and the planet over here is glowing in millimeter wavelength emission, which is not really the emission from the planet. It's more likely to be pebbles or dust in the vicinity of the planet in a circumplanetary disk, kind of disk that probably gives rise to moons like the Jovian moons of Jupiter. So maybe a little planetary system writ small around the planet.
Transit method of observing planets. It strikes me that that must be a very, very small population of the planets, of the whole system, because you have to see it on plane.
Ah,
You
it's so true.
can't observe it on flat.
Yes, exactly.
The question is that a statistically representative sample that we can actually infer to the rest of the systems?
Great question.
Can you repeat the question, please?
Yes,
Yeah, so
sure. The question is, when we talk about detecting a planet through a transit, then we put it on a diagram like this. Is it a fair representation of all the planets out there? Because in order to detect the transit, we need to be in a very specific orientation where there's the planet, there's the star, the planet, and us. The three things have to line up, which isn't that easy. So the fact that people can detect so many planets with transits, of course, they've looked at many stars. But the fact that you can detect so many planets with transits means that there are even more planets out there, because the probability of getting the lineup of our planet and you is a few percent of the total, possible viewing geometries. Whatever you see, you need to kind of multiply by the other part of the sphere that you were not sensitive to. That's what people do when they try to figure out what are the true demographics of planets. So here I was just showing the ones that have actually been detected, but you're absolutely right. These planets must be pretty common for us to see so many of them.
actually, the graph that you just showed, that most of the masses were closer to their central star than in ours. Does that say anything about the relative age of those solar systems versus ours? They may have had longer to migrate inwards towards their central star.
Those are excellent questions. So if we could, when we look at thanks, Claire. When we look at a diagram like this, we infer from anything that's here the history of planets, where they've been, did they migrate, how far did they go, where did they start. What we would really love to see is to be able to take a snapshot, to be able to survey planet formation as it's occurring. At the first instance, 100,000 years later, 100,000 years after that, and see where the planets moved. Pretty tough, because first we'd have to figure out, all the details of how to connect these things up because you're only looking at each thing at one slice in time. So the kinds of things that astronomers can do are probably to look at very young forming systems like PBS 70b, if we could make a big inventory of those. And then maybe look at systems that are quite a bit older once their disks have dissipated, see what are the orbital distributions of those planets, have they migrated much since then? Those are the kinds of things that we probably can do, but it's a little bit in the future. But those are the ideas of what people would really love to do. The moment we just have a snapshot and we have to use theory the way to try to back it out and see where things could have formed and gone. Question here? Yep.
There may be particularly in diversity, we were able to see now in the more environment about that time. So that's thanks really challenged. Kind of for the iron, but
Oh, there are just so many. There are so many. What are there any big controversies that we really want to see resolved? And there are so many. Like one thing that we maybe don't have a really good idea about is when we're counting up these planets, like when we're talking about, hey, we're doing a transit planet. That's a particular geometry, and if all the planets were in a plane, like in our solar system, we could see how many transits we're getting and then know all the planets in that system. But if they formed with a lot of different inclinations, so here's a star, but some are planets are orbiting like this and some are like this. Even if you detect one transit, you won't detect all the others. People are trying to figure out whether, when we say we've detected so many planets, that there must be more than one planet per star, because most of them are all in one system. Like one system has 10 planets, nine out of 10 systems have no planets. A little hard to tell the difference between those kinds of things. So those are the kinds of this is a pretty minor example that I'm giving. I should probably be able to come up with a better one. But that's just an illustration of what we know and don't know.
It's the speed of the exoplanets relative to the distance from the star and the mass of the star. Or
Yes, I mean they follow Kepler's laws, the sense of gravity, that kind of thing.
so the closer planets, so
Are orbiting more quickly. Yep. Mhm.
Why did our solar system stop making planets?
Why did our solar system stop making planets? That's a good question. So in the story of core accretion, we start with the small grains and then we eventually build the planets. And eventually gas in the disk dissipates because it's being irradiated by the star and things like that. So there's a time limit over which you have to make a Jupiter if you want to be able to make one, because you lose all the gas that you can make a Jupiter with. So that's one reason. But in principle, things like smaller planets that don't need a lot of gas could form over much longer timescales if you have the resources available. Well, the picture of the formation of the Earth, for example, we may have gotten to be like Mars size, really, and while the disk was still present. But after that, the rest of the Earth may have assembled through subsequent collisions, and a final collision that created the moon, for example, might be one example of that kind of late planet forming thing that's like 100 million years after the beginning of the solar system. But generally, we run out of resources to forming planets.
are you able to take enough data to say anything about the temperature of these different exoplanets?
Yes. Okay. So are we able to measure the temperatures of exoplanets?
That's said anything about the possibilities of life. In which you first need to know the temperature.
Right. So what are the temperatures of exoplanets, and do they have the conditions necessary for life? So people actually try to measure the temperature. One way we can measure the temperature of the planet is when you look at the integrated light. You have a planet, you have a star and planets going around, and you look at the light that are missing when the planet goes behind the star. That decrement is the light from the star of a planet, sorry. And that can give you a sense of how hot the planet is, because if it was hotter, it would be brighter, etc. Do planets have the conditions necessary for life? That is a major that is a major I don't know if it's a controversy. It's a major desire people to try to figure that out. And so people are using the James Webb Space Telescope and other facilities to look at the composition of planetary atmospheres. One way to do it is when the planet goes in front of the star and you're seeing the planet plus its atmosphere. You can look at the light through a transit through the atmosphere and measure the chemical composition of the atmosphere. That's one of the methods that people are using.
Related to that question, and we assume that the possibility of life is relative to the temperatures on Earth that support life.
So when we think about the origin of life, we're talking about planets that are only roughly the temperature of Earth. So like in the Goldilocks, what's called the Goldilocks zone, where we have liquid water and the right temperature. Yes, I mean, we are certainly one terrific example of a planet that can actually produce life. So people are really keen to look for other planets that are like that. But, when we look at extremophiles on Earth, it's pretty clear that you can create different kinds of life that have different kinds of metabolisms that could exist in much hotter or much colder environments, or higher or lower irradiation environments. So people are really trying to take a broad look at that kind of a question.
Why do different planets form with like different chemical composition in their atmosphere?
Oh my goodness. Okay, another controversy. Okay, what determines the chemical composition of planetary atmospheres? Okay, we're talking about something like Jupiter. The composition is the product of all the places that it's been. So in the story of Jupiter, we build the 5 to 10 Earth mass core. Wherever it formed, those solids are making up the chemical composition of the core. Then it's going to try to enrobe itself in some large amount of gas. And what it's going to collect depends on where it goes. Depending on where it is in the disk, different kinds of molecules may freeze out, and that affects what's left in the gas. And Jupiter's composition is the product of everything, all the places that it was when it was accumulating its atmosphere.
Last final question. If you could have one new source of data to help you out, where would that come from? What would it be?
If there was one new source of data to help me out, where would it come from? That is such a hard question, because I think each person might have their own answer here. One of the things about this whole topic is that there's so many ways to make progress. We could try to detect more planets further away from their stars, more like the solar system. We're trying to do that. We would love to measure the chemical composition of those planets, to know whether they were like our solar system or not. I would love to also know the inner disk composition of where planets are forming. What kinds of materials does it inherit? I need to also know what features to look for. So I need some laboratory spectroscopy to help me out. Just so many things. But also, I think that means so many ways to make new breakthroughs. Sorry, I can't give one answer.
What happened?